So and then what we need to do is we solve the momentum thickness. So the idea is we have this equation, and then the idea is we have u to the power of 6 at this one, at this area. Please do not substitute the value of u inside this equation. So we are using this equation into the integral parts only. So we substitute it here. We do the integration 0 to x 2 dx. So we have this term. So and then because it is too long, so sometimes we assume that the total of this one is equal to a. So and then we could write as theta square is 0.45 nu to the power of u6, and then the value of here is a, so we could have the a here. Okay, so we don't have this one, I think. So and then we solve the lambda here. So we have the lambda theta square over nu du dx. So we substitute the value of theta square here. So we get the value of theta from this one. So we have a 0.45 nu a over nu u to the power of 6. So we have a du dx. So and then from the du dx here, again, we substitute with the velocity that we get from the question here. So we have 1 over x, and then if we solve it, we could get this one, and then we could simplify it as negative 0.9 xa over u to the power of 6. So and then we believe that from the previous research, so the separation occur at lambda is equal to negative 0.09. So and then we substitute the value of a. So this is the value of a, and then we could simplify the value of x here. We could calculate the value of x here by at lambda is equal 0.09, negative 0.09, and then we find that it is x equals 0.268 meter. So what is the meaning of 0.268? Means the separation occur at 0.268 meter. For flow that fit with the velocity profile of 1 minus x squared. So this okay, the calculation here may be a little bit difficult to do. So normally people will do any numerical methods. So normally for simple calculation, we could calculate by using the Excel. So means that we just to make sure to get the value lambda negative 0.009 here. So we get the value of x later on. So for example here, if we plot the graph, so we could get that the value that occur here, which is the negative 0.009, it is around 2.6 something. Okay, here. So again, the calculation is not straight forward. So means that it is not just you substitute the value and then you get the final answer, because at this stage, all the evaluation of boundary layer is actually conducted by curve fitting, as I show you in the previous graph. So previous researchers do a lot of analytical works and experimental, and then they comes out the equation by the curve fitting. So it is not just the simple equation that comes from the derivation. So and then what I want to show you here is the Thwaites method for asymmetric flow. So as we know, we have the Cartesian coordinate and also the polar coordinate. So this is the idea of polar coordinate. So sometimes it can be used when we solve problem of a rounded object. For example, just a bullet here. So, or the submarine or something, or flow in nozzle, convergent and divergent nozzle. So we have the function of r here as the radius. So and then the function of theta actually here, the angle. So the equation, okay, will become like this one. So I hope you could remember this one. So I try not to forget to give this equation in final exam or in test 1 and test 2. So the Thwaites equation can be written as this one: 0.45 nu r square over r square u to the power of 6 and integration a to the 6 r square u5 dx. So for potential free stream flow past a sphere, the velocity distribution is given as u 1.5 u naught sine x over a. So this is all the simplification. The r naught here means the maximum one. So this is the a sphere. So this is the stagnation point, and then this is the inlet velocity of stream. So we have the du over dx. So we substitute the u, so we could get this one. So and then this is the equation for the Thwaites equation. So and then we have here, so we have the equation of 0.46 r square u6, integration of this one, and then we substitute the value. We do the integration, and then we get this one. So and then finally we could have the final equation of this one. So we determine the lambda. So it is following the same step actually. So we have a du dx at equal of this one. So and then we substitute everything. So we finally we could get the lambda here. So and then to simplify, so you could have the lambda as this one. So we assume that x over a is equal to x, and then we could simplify the terms of this one. So and then we make a graph from the Excel, and then we could get this one, and finally we could say that the negative 0.09, the value of lambda here will trigger the value of angle. So this is the angle. Okay, so it is around 100 and okay, I'm sorry, 100 and something. I think based on this, lambda is 0.09, is 103.6 is the location the separation was, the separation will occur. So and then this is the idea, just a note here, the plane laminar wake for field approximation. So this is the idea is sometimes the wake is not occur at this one, so it will occur at the back of the aerofoil. So this is what actually occur when the separation start to have from here. So and then but the wake can be oscillate like this one. So this is not the formation of wake is actually not the syllabus of this one. I just limit the separation because this is the quite the direct influence of a boundary layer. So and then for the wake, you could calculate by using this one. So again, this equation is actually comes from the experimental work and the analytical. So and then the researcher curve fitting, do the curve fitting, and then they will comes out with the with this equation. We will discuss a few questions from the textbooks that fit into our syllabus. So for example, we go for question 4.1 here. Velocity profile is given as follows. U over U equal 3 over 2 y over delta minus 1 over 2 y per delta cube. So and then we need to calculate we need to compute or calculate this item. So we need to calculate the delta over x naught, or the value of theta, the value of delta star, the value of delta, CF, and also CD. So for CF here, it is actually equivalent to C with a small d. So it reflects the coefficient of local friction. And then the capital D here is the drag coefficient for the whole object. So and then I would like to share with you, I think you already know, if we use the idea of eta here. So to calculate the delta star, we have two type of equation. One is 1 minus u over u dy, and then we could change into the eta as shown as this one. So the integration of 0 to 1 minus f eta delta d eta. So normally that's why if we see solution made by Blasius and so on, they will always use the eta, because the calculation of eta is actually could simplify the long equation. We could do integration work easier. So these two equations, I think you already know when you learn boundary layer in final year in undergraduate last time. So and then let's say we have u over u as this one, and then we could write is as eta, mean we change the value of y eta here, y per delta into eta, so we have this one. So and then we have two terms. One is 1 minus f eta, so and the another one is f eta times 1 minus f eta. So if we do this one, so we could get this term. So and then we could calculate the value of theta here by substituting the value of this one, and then we integrate into d eta here. So and then we could get the value of theta is 39 over 280 delta. Okay, you could do and then to calculate the theta, to calculate the theta and also the delta, we could start from the Newton's law of viscosity. So we have this term, tau is equal mu du dy at y equal to 0. And then from this equation, we could calculate the value of du dy at y equal to 0 as 3u over 2 delta. And then we substitute into this one. So now we have two value of theta, okay, and then one is from the von Karman. So this is from the Newton law of viscosity, and this is from the von Karman. So we substitute the value. So we substitute the value of theta here, 39 over 280 delta. So we have equation 1 and equation 2. So and then we equalize equation 1 and equation 2 like this one. We integrate both sides, so and then we could get this term. So we have a constant here because of the integration. So and then we substitute the value of x equal to 0, delta is equal to 0. I think you know about this. So it is about a flat plate like this one. So if this is the boundary layer, so means that at point here, at x equals to 0, the boundary layer thickness is still not occur, so it's equal to 0, then the constant is equal to 0. And finally, we could determine the value of delta is 4.64x over square root Reynolds number. So, and then we could calculate the value of delta here, the value of theta here by substituting the value of delta here, and then we could get it is equal to 0.646x over square root Reynolds number. So this is, we could calculate the delta star, and then we could get it is equal to 1.74x over square root Reynolds. So, and then if we want to calculate the shear stress, so we could have this one. So, okay, so this is the shear stress. So, and then we have, we could calculate the delta as this one. So, I think you could do this at home. So, and then to calculate the CF here, so we are using this equation. So, we substitute everything that we have. And then sometimes, please, if you have a square root Reynolds, so please expand the square root Reynolds number as this term, because we could simplify the value of rho and u from the equation of Reynolds number here. So we could get the CF as 0.646 over square root Reynolds number. We could calculate the CD. So I think I already explained this one. So we could get the value of CD as this one. We substitute into the equation, and finally we could have the value of CD as 1.292 over square root Reynolds number. Okay, next we go for next question. So from 4.3, so we have a simple flat plate velocity profile assumed as this one, u over u sine pi over 2 y per delta. So, and then we need to compute, verify by computing the CF here. Okay, so again, you could do this at home because it's very simple. You have a u over u here. Yeah, you just substitute the value of u over u here in the equation of delta star and theta, and then you equalize. You do the integration between two value of shear stress, one from von Karman equation and another one is from Newton's law of viscosity, and you will get the value of delta here is 4.795x over square root Reynolds. Okay, so the idea is simple. So this is the equation of von Karman equation. You have d theta dx. So to find the theta here, so we substitute into this equation. So we substitute into this one. So, and then we could get the value of tau is equal of this one. So, and then this is the equation from the Newton's law of viscosity. So please make sure that you substitute the value of y is equal to 0. And then we could get the tau is equal to mu u pi over 2 delta. Then we equalize equation 1 and equation 2. So we could have this one, and we do the integral for both sides. We could get delta is equal 4.795x over square root Reynolds number. We could calculate the shear stress from the from the value here from the Newton's law of viscosity. So we could get this one. We could calculate the local coefficient of drag CD, and you will get this value, and then we could calculate the CD here, so you could get this value. So I'm not explain this one because I think this is just there. You could do this at home. Okay, we go for question 4.4 here. So air at 20 degrees Celsius and 1 atm flows past a smooth flat plate as shown in this figure. a pitot stagnation tube placed 2 millimeter from the wall develops a water manometer head H equal 21 millimeter. So H is the here. So means use this information with the Blasius solution, table 4.1, to estimate the position X of the pitot tube. Check to see if the flow is laminar. So this is the idea how we could determine the pressure profile on the flat plate. One is idea by using the pitot tube like this or the U-tube manometer. So the idea is when the fluid or the air flows inside this tube, so they will push the manometer fluid here. I think you already know about this. So it will give a difference of 21 millimeter here. So based on this pressure, we could assume that what pressure and velocity occur at this point. Okay, so and then we need to estimate by using the Blasius solution. Okay, and then we could determine the value of X. Okay, to simplify this calculation, we assume at 20 degrees Celsius, 1 atm, the density of air is 1.205 kilogram per meter cube, and the dynamic viscosity is this one. And then the question is estimate, first we need to estimate the velocity at y equal to millimeters. So means the velocity at this point. Okay, so we could assume this by using the Bernoulli equation. Let's say the air flow from here to here. So let's say this is point number 1 and this is point number 2. So and then we could have Bernoulli equation for that point. Let's say we have P over rho G plus V square over 2G plus Z. So I think you already know the equation here. So and then we could simplify it because the level is the same, so we could assume that Z1 and Z2 is equal to 0. And then because the velocity at point number 2 here will become stagnation velocity, so you could imagine that when the air flow inside this tube, so after certain time, so the air will trap on this tube, and then it will fill the tube here, and then it will become a solid body. So means that there are no more fluid could go through inside this tube. So at that time, the velocity will collide at this entry point. So the velocity is called as the stagnation. At that area will become stagnant. So we call that point as a stagnation point. So at stagnation point, the velocity is 0. So we could assume that velocity at point number 2 here is equal to 0. So and then so we have okay, at P1 here, we could assume that it is equal to P atm. So we could take we could calculate this calculation as a gauge pressure. So the atmospheric pressure can be assumed as 0. And then pressure at point number 2 here. Okay, so pressure at point number 2 is equal pressure at point number 2 here can be calculated by using this U-tube manometer here. So it is equal to the rho GH of this height. So we could calculate that it is equal to rho GH, so the rho of fluid. Okay, so the idea is, so let's say okay, the fluid here is equal to water. So to calculate, so means that the pressure that act here is equal to the pressure at this point. So the pressure at this point can be calculated by the rho GH of this one, because the fluid inside this gauge is water. So we need to calculate the pressure at that point as rho GH of water. So we use rho is 998, this is the gravity, and this is the height of the manometer head. So and then we could calculate the pressure of PA, which is equal to the pressure at point 2. So it is equal to 205 Pascal. So and then, so how we could use the pressure here to estimate the velocity? Because in this Bernoulli equation, we assume that the velocity at point number 2 is stagnant. So means that there are no velocity. The velocity is 0. However, the pressure is 205 Pascal. So we know that if we take out the U-tube, the pitot tube here, so means that the pressure of 205 Pascal here will be 100% converted into kinetic energy, because at this point the fluid will flow at maximum velocity. So by using that idea, we assume that we need to convert the pressure of 205 Pascal here into velocity. So the idea is, so this is the Terrisoli theorem. So normally we could easily calculate the velocity as square root 2gh, or we could see here, this is the pressure is equal to rho gh, and then if we see the equation for velocity is v square over 2g. So means that if the pressure here is equal to the velocity here, so we could say that p over rho g is equal to v square over 2g. So and then we convert the calculation of pressure here with rho gh. So means that the value of rho g can be cancelled. So we have an h here. So and then the velocity can be calculated by using 2gh square root. Okay, so that's why we get this equation. Okay, that is the idea of Torricelli theorem. So however, we cannot use the height of 21 millimeter here, because this 21 millimeter is measured by using a water inside this tube. We need to change the perspective by using the air. So it is very simple. So if the pressure 205 Pascal is created by air, so the height will become 17.34195 meter. So we use this height to calculate the velocity of air. So from this equation, we substitute the height of 17 meter, and then we could get that the velocity V2 is equal 18.45 meter per second. So and then, how to predict the value of x? Because in this problem, we are not calculating velocity or pressure on the surface. It is actually 2 millimeters from the surface. So we use the idea of Blasius, because Blasius table will give us the ratio between U and capital U. So we determine the ratio. So we know that the U is 18.45. So the capital U means the velocity at the inlet here before it flow on the surface. So it is 20 millimeters, 20 meter per second. So the ratio is 0.9225. So from this value, we could see the Blasius table of this one. So we know that the f prime here is equal to u over u. So you could refer from the in previous lecture notes. So from this table, so we find the value of 0.9225. So we have 0.90 and 93. So we could do the interpolation calculation. So we have the 0.90 and the eta is 2.5. we have 0.93, eta is 2.6. So for f prime 0.9225, so the value of eta is 2.5451. So we know from the equation here, so eta is equal y rho u over 2 mu x. So you could refer from the previous calculation, previous lecture. So we could calculate the value of x is equal to 41 centimeter. So and then we could check the Reynolds number. So we calculate as rho Vd over mu. We substitute all the value. Okay. So for diameter here, you just replace with the value of L. So rho VL over mu. So we substitute the value of 41 centimeter or 0.41. So we found that it is 5.46 times 10 to the power of 5. So normally for smooth plate, we could assume that this is just a borderline, because normally we take 5 times 10 to the power of 5 is the transition from turbulent to Reynolds number. However, as I said, people will take 10 to the power of 5 is the fully laminar, and 10 to the power of 6 is fully turbulent. So and then why? Because for flat plate, the transition is quite longer. So at this region, the transition between the laminar and turbulent occur. So the idea of transition means the percentage of turbulent boundary layer will increase from 1% to 100%. So normally people will take the center line. So that's why we take 5 times 10 to the power of 5 is the transition between laminar and turbulent boundary layer. So we neglect the existence of transition. So and then about the surface roughness here. So it will influence the formation of turbulent boundary layer. So for the smooth plate, so we could say that the laminar still occur until 10 to the power of 6. So and then the transition only occur at this point. So later on in chapter 5 and chapter 6, we will learn about how to determine or how to substitute the parameter to reflect the surface roughness for Reynolds number. Okay, so this is tutorial 4.11. So a thin equilateral triangle plate is immersed parallel to a 12 meter per second stream of air at 20 degrees Celsius and 1 atm. As in figure 4.12, assuming laminar flow, estimate the drag of this plate in Newton. Okay, so in this situation, we have a triangular plate, and then we have a free stream velocity from left to right flow as shown in this figure. So the problem of this calculation is actually our plate here is triangle. So means the triangle plate means the calculation must be conducted in integral calculation, because you could imagine that at this point, okay, the fluid flow from here to here, and the length is the longest one. But at point here, so the fluid only flow until this point, and for this point, the fluid only flow with a short distance. So means that because the distance is not similar, so we need to calculate this using the idea of integral. So another thing that you should understand about this, for example, if we have a delta wing aeroplane like this one, and then we have the incoming or free stream velocity like this one. So in real situation, the laminar boundary layer will change into turbulent boundary layer, but okay, maybe the changes is only occur at the bottom like this one, because maybe the flow from here is laminar, and after this point the separate it's changed into the turbulent. However, for this, for flow at this area, because the distance is short, maybe it will only have laminar boundary layer. So means that from this point, so we need to calculate that the laminar and turbulent boundary layer in our calculation. But for this region, we only calculate the laminar boundary layer for lift and drag calculation. Okay, this is the situation or the complexity of this shape. Okay, so because we don't know the velocity profile, so we just use the Blasius exact solution, because the question is assumed it is a laminar boundary layer. So from the Blasius exact solution, we know that the CD is equal to this equation. So and then we could calculate the value of the direct force by using this equation. Okay, the problem is, as I said, because the area is not symmetry, so we start with the small area of this one. So let's say we have a rectangular, very thin area of this one, and then we assume that this is our origin, 0, 0. So the total length, so let's say we start with the half of this triangle. So the length is 1.73205 meter, and the height here is 1 meter. I think you could easily understand by looking this dimension. So we have the height is 2 meter. So you could calculate by, because the length here is the same, so the angle here is 60 degrees. So you could calculate all of this number. So we could calculate the drag force for that particular area. So we know the value of CD. So and then we could get the value of FD is, so this is the value of the small area. So we substitute everything, so we will get this term. Okay, so and then we could calculate the total drag force by integrating these terms left and right. So we could get the DFD will become full drag force here. So and then we integrate the value here with DL. Okay, so Y here will become DL. So and then we substitute the limit of 0 to 1, 73205, because normally you are advised to calculate only for the half triangle here, because the direction here is reverse. I'm afraid that you will get the value of 0 if you do integration from 0 to 2. Okay, and then because we are focusing on this line, if you do the integration of 0 to 2, maybe you are assuming that the triangle is something like this. Okay, please be careful in your calculation. So if you do the one here, so and then here the value of dy here needs to be changed. So the idea is L maximum is 1.73 and Y max is equal to 1. So and then it is equal to L over 1. L over Y. So and then if we do the dy dl, so I think you could simply put dl dy here. So we could write as dy is equal to 1 over 1.73205 dl. So that's why we substitute the value of this one. Okay, to substitute the value of dy. So and then we do the integration, so we will get this one. We substitute all the values. So this is the density of air, the dynamic viscosity of air, and the U is equal to 12 meter per second. So and then we could get it is 195.44 Newton. So please bear in mind that that calculation, it is only for this triangle. So because we have another part, so we need to times 2. So if you are calculating this from your experiment, so means that the boundary layer will occur at both sides. So mean it will occur on this surface and also at the back. So means that you need to multiply again with 2 because it will reflect the total force that occur on that triangular. So this is question 413. We have a flow straightener consists of array of narrow duct placed in a flow to remove swirl and other transverse secondary velocity. One element can be idealized as a square box with thin side as figure 4.13 as this one. Using flat plate theory, derive a formula for the pressure drop delta P across an n times n bundle of such boxes. So flow straightener here. So another terms that normally used for flow straightener is actually the honeycomb. So I think for somebody who do experiment using water tunnel or wind tunnel, so we need to straight to make sure that the flow inside the wind tunnel is straight. So we use the flow straightener. So the flow straightener, or another word is the honeycomb, is the arrangement of small boxes like this to make sure that the flow is straight. Okay, the simple one to create our flow straightener is by put a straw. Okay, for example, you have a frame like this one. Okay, a frame like this one, and then you put a lot of straw inside this box. So and then it will become a flow straightener. But for high quality flow straightener, so the shape of the small box is actually similar with the honeycomb. So that's why we call that the honeycomb. Okay. So because we focus on the laminar flow first, so we assume that the flow inside that box is laminar. So we could calculate by using the Blasius exact solution. We could get that the CD is equal 1.328 over square root Reynolds number. So and then we could calculate the drag force by using this one. So and then here we have the CD 1 over 2 rho AU square. So the A here is actually the area of this one. So according to this diagram, so if the width is A, okay, and the length is L, so we could get the area is A times L. So this is actually the drag force that occur on this single plate. So means that for this situation, we will have 1, 2, 3, 4. We have 4 surface inside. So means that we need to multiply with 4 in our final calculation. Okay, calculate the drag over 4 wall and n box. So n square means normally we assume that we have a big area like this one. So and then we put the same a small box here. So and then because the question is n times n, so we use the idea of n square boxes here. So and then we multiply with 4, so we get this idea. So and then we know that the pressure is the force divided by area. So we have the total forces, the total force here divided by the area is NA square. So and then we have the value of this one. Okay, so we have the pressure is the value of this one. So this is question 4.50. Air at about 1 atm and 20 degrees Celsius flows through a 12 centimeter square duct at 0.4 meter cube per second. As in figure 4.50, 200 thin plates of 1 centimeter chord length are stretched across the duct at random position. They do not interfere with each other. How much additional pressure drop do these plates contribute to the duct flow loss? Okay, this idea is actually something like this. So we have a flow, a duct here, a square duct. Okay, so and then inside these square ducts, they will put a thin fin like this one. So it's connected from wall to wall. Okay, so and then the idea is when the air flow inside this one, so it will create boundary layer on this one, on this plate, and then you know the boundary layer is actually the resistance. It will change the velocity. So when you give a lot of resistance inside a pipe, inside a duct, so means that the pressure will drop. So this idea is actually we could drop a pressure for a fluid flow inside a duct without having too much phenomenon like turbulent wake and so on, because the plate is very thin. So and then the idea is it is not interfere with each other. So normally, so the location is actually it is separated from each other to make sure that the flow is remain like a normal flow. Okay, so and then it gives us the flow rate is 0.4 meter cube per second. So we could calculate the velocity. So we know that Q is equal to AV. So the velocity is the flow rate divided by the area. So the area is 12 centimeter times 12 centimeter. So it is 0.12 times 0.12. So we have 27.8 meter per second. So and then if we check this one, so the Reynolds number is 222,000. So means that it is turbulent. So here, please make sure that you are using a correct transition limits. So for square duct like this one, so it will follow the idea of flow in pipe. So for flow in pipes, if the Reynolds number is larger than 2000, so we could assume it is turbulent. But sometimes you could take the Reynolds number is larger than 4000. Okay. So because it is 200,000 here, so we assume that the flow is turbulent. So we could use the common value of flow in pipes and the common value of CD of turbulent. So and then we need to calculate what happened on the plate. Okay, because the plate is very short, 0.01, and then we calculate the value of Reynolds number here, so we get it is 18,000. So again, you need to understand the phenomenon, the situation, and choose the right limits. For that thin plate, so the flow that occur on this plate is reflect the flow on flat plate. So means that the transition from laminar to turbulent must be using the idea of flow on flat plate. So means that if this Reynolds number is less than 5 times 10 to the power of 5, so means that the flow is remain laminar. So here, please be careful, because here we are using the idea of flow in pipe because we are evaluating the flow inside this duct. So and then when we evaluate the flow on this fin, we need to use the idea of flow on flat plate. So we need to use the limit of this one to determine whether it is laminar or turbulent. Okay, because it is laminar, we are using Blasius exact solution. So this is the CD. So we could substitute the value of Reynolds number here. So and then it is equal to 0.00976. So and then we could calculate the drag force for one plate. So we could calculate by this one. So and then we could multiply with 200 to get the total force of 280 Newton. So and then a free body of the plate shows that this force can only be balanced by an overall pressure drag across the array of plate. So means that the delta P is total of force divided by the cross-sectional area of A. So and then it is equal to 151.4 Pascal. So this is means that the so this is the pressure drop that occur on that area. Okay, this is question 4.52. A conical diffuser of initial radius r expand at a uniform angle theta, as in figure 4.52. The flow enters at uniform velocity u theta. Assuming a one-dimensional free stream, use any laminar boundary layer method of your choosing to estimate the angle theta for which flow separation occurs at x equal to r. So this is the conical like this. So and then it has a maximum r in the inlet like this one, and then it expand at certain angle. So and then what we could do is first we need to determine the velocity profile. So the velocity profile can be determined by using this idea. The flow rate for inlet and outlet must be the same. So we assume that it is incompressible fluid. So because we don't know whether it is compressible or incompressible, so to ease this calculation, we assume that it is incompressible. So we just equalize the flow rate at inlet and outlet. So we have this one. So and then because the flow rate at outlet here is expanding, so we use the idea of small r for the point number 2 here. So and then we could get that u, small u means the velocity at the second point here can be written as capital U, which is the free stream velocity here, times r square divided by r square. So and then to simplify our calculation, we could draw this one. So means that this is the triangular. So and then we have the idea of this one. So because it says that, so this is the starting point. This is the starting point, and then from the question, the separation is occur at 2x here. So we just assume that this is the length of 2x, this is the r, and this is the angle theta. So from this diagram, we could say that angle of A, D, and E, DAE actually. So we could calculate the tangent is r over 2x plus f. And then for triangle A, B, and C, so the theta is r divided by f. So and then from this one, so we could simplify it from equation 1. And then the f here is the r divided by tangent theta. And then from 1 and 2, we could simplify the value of r as this one. So and then we change the value of tangent theta with r over f, and then okay, so and then we could have this one, and then so we simplify this one as kx, and then we have k is equal to tangent over r. So and then because we need to estimate the separation, so we are using the Twit's equation. So for Twit's equation, we have two equation. One is for Cartesian coordinate and another one is for cylindrical coordinate. So because we are solving the cylindrical shape, so we use the polar coordinate like this one, and then we substitute the value of u here with the velocity profile of this one. So again, and then we change the u here with the u, we just remain this one. So and then we substitute the u here, and then we do the integration of dx. So and then we substitute, we change the term into the k plus x, 1 plus kx to the power of 10. After we multiply, we solve the power of 5. So we have this term, and finally we have this one. So and then we know that u is equal of this one, so we do we differentiate with du dx. We have this term. So and then we could calculate the value of lambda by having this one. So lambda is theta square over nu du dx. So we substitute the value of theta square from the calculation here. So we have a theta square over nu. So and then we substitute with du dx here, and then we get this one. So and then we from the correlation previously, the separation occur at lambda is equal negative 0.09. So and then we could substitute the value here. Okay, so and then we could get that the theta is equal 1.13 degree.